للعالمين.
All right. So we are back, and if the goal ultimately today is to have a better understanding of things like strings so that we can solve problems with text, let's consider some simpler types of data first, how we might represent those, and then see if that doesn't lead us to a discovery as to like how strings in just today's modern software is using things like that. So when we talked on week 0 about representation of data, we had different ways of doing it in terms of binary and decimal and unary even. When we started talking about the same last week in code, we started talking about data types instead. And these data types were a way of telling the computer, like, do you want an integer? Do you want a character? Do you want a floating point value, like a real number, or even a string, as we've seen? But it turns out that computers, of course, only have finite amounts of resources. Your computer only has a fixed amount of memory or RAM, and that actually has very real-world implications. So for instance, here are some of the data types we've seen thus far. And it turns out that each of these in C has a specific number of bits allocated to it. Now, admittedly, this can vary by system. It's not so much the case nowadays, but for many years, for decades, computers were getting better and better. The earliest computers might have used fewer bits for some of these data types. More modern computers might use more bits. So the numbers you're about to see are pretty much where we are present day. So when it comes to these data types, a bool, which is true or false, somewhat curiously uses a whole byte, even though that's way overkill. Because for a bool, true or false, you of course only need 1 bit. But it turns out, even though it's wasteful to use 8 bits or 1 byte just to represent true or false, it's just easier for computers. So a bool tends to be 1 byte. An int, which we've been using a lot, uses 4 bytes typically, or 32 bits. And if I do some quick math from week 0, with 32 bits, you have 4 billion possible values, roughly. But if you want to represent positive and negative, that means you can represent roughly -2 billion all the way up to +2 billion. So that's the range typically with ints. If that's too few numbers for you, turns out there's things called longs, and longs use 64 bits, which allow you to have like a quintillion number of possibilities, which is a lot, certainly a lot more than 4 billion. So sometimes you might use a long. But even that's finite. And so, as we discussed at the end of last week, bad things can happen if you make certain assumptions as to data because of things like integer overflow or the like, where things wrap around. Then there's a float, which is a real number, something with a decimal point. By convention, it's 4 bytes or 32 bits, which gives you, in short, only a specific amount of precision. It doesn't necessarily dictate how many numbers to the left or to the right. In the aggregate, ultimately, you have, though, 4 billion possible permutations still. If you need more precision for scientific, for medical, for financial applications, you might use 8 bytes, aka a double, which just gives you more digits of precision. They eventually get imprecise per the example we looked at last week, but it at least gets you further down the line. As an aside, in really, really important applications in finance and medicine and military operations and the like, where you really can't have rounding errors, long story short, humans have developed libraries in C and other languages that use more even than 8 bytes. So there are solutions to these problems, but they're always finite. You have to pick an upper bound. Then there's char, which we saw briefly last week when I asked the user for y or n for yes or no. And then there's string, which I'm going to propose as a question mark, because a string totally depends. Like hi, h, I, exclamation point would seem to be 3 bytes. D-A-V-I-D would seem to be 5. So strings clearly are variable based on what you or the human type in. So we'll see what this means, though, in just a bit. This, though, is the thing inside of your Mac, your PC, your phone. Might not look exactly like this, but this is a memory module for a modern computer. And let's go ahead and use this really as just representative of the finite amount of memory that any computer indeed has. Let's zoom in on one of these little black chips on the circuit board here. Zoom in, and let me propose that this rectangle really represents some number of bytes. Like tucked inside of this little black circuit on the board is maybe, I don't know, a gigabyte, a billion bytes, maybe it's 100 bytes, some number of bytes. It totally depends on the computer and how much you paid for the stick of memory. But if there's a finite number of bytes, physically implemented somehow digitally inside of this hardware, well, then it stands to reason that we could number those bytes. We can just arbitrarily decide that the top left corner is byte number 1, or really byte number 0. The one next to it is number 1, then number 2, number 3, dot, 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 number 2 billion, or whatever it is, however big this memory is. So if you use a variable in a C program that's only 1 byte, like a char, it might literally be stored in that top left-hand corner of the memory. Like in practice, you don't care where physically it is. But really, the artist's rendition would be this. A char might use one of those single bytes somewhere in the computer's memory. If you use an int, which is 4 bytes, it would give you 4 bytes, contiguous, that is left to right, top to bottom, but all 32 bits would be next to each other. So the computer knows that those indeed all belong to the same int. If you need a long, or a double for that matter, then you might use a full 8 bytes in this case. And you just keep using and using this memory, kind of like a canvas, almost in Photoshop or a spreadsheet, where you can just move pixels, or you can move data around. That's really what your computer's memory is, a canvas for storing information in units of bytes or 8 bits. Now, we don't need to keep looking at these circuit boards. We can abstract it away, as we often do. And let's go ahead and zoom in on this grid just to consider some very specific variables. So let me zoom in. And now I see fewer but larger boxes on the screen, each of which, again, represents a byte. And now let me propose that we play with some actual code. So here in C, albeit without a full program, are 3 ints, score 1, score 2, score 3. I have coincidentally given myself two scores at around 72 and 73, and then a pretty low score at 33. Of course, last week or 2 weeks ago, this would have been high, but now we're dealing with actual integers. So these are 3 so-so scores on my quizzes or tests or the like. So let me go to VS Code here, and let's make a program called scores.c. So I'm going to write code scores.c. That's going to give me my new file. And let me go ahead and implement something like this. Include standard io.h, int main void, and then inside of here, let me do int score 1 will be 72, int score 2 will be 73, and int score 3 will be 33. And then let me just do something like write a program to average my 3 test scores together, something like that. So let me do printf, quote unquote, my average is, and I'm going to go ahead and do, say, %i \n. And now let me plug in the results. And this is kind of grade school math now. How do I compute the average of 3 values? Well, just like on paper, I can do score 1 plus score 2 plus score 3 in parentheses, because of order of operations, divided by 3, since there's 3 total scores. All right, so I think this checks out. And indeed, you can use parentheses and operators like plus in your code like this in C. Let me go ahead now and do make scores. No syntax error, so that's good. Nothing missing there. And now let me do /scores and see what my test average is. All right, it's not great, but I think I still passed. And indeed, my average here is 59. Is it precisely 59, though? Well, let's see. Let's actually, instead of using an int, how about we go ahead and use something like a floating point value here. And let me go ahead and do this. So let me recompile my code, make scores. All right, I've got an issue. Let me zoom in on my terminal window. We've not seen this one necessarily before, but error on line 9. Format specifies type double, which is a lot of precision, but the argument has type int. So what does this mean? Well, it's showing me with these green squigglies that something's bad between the %f and this thing over here. Well, on the left, I'm implying a float, or a double for that matter. On the right, though, what data type are score 1, score 2, score 3? All right, so they're ints. So Clang does not like this. The compiler just doesn't like that I'm using ints on the right, but I want floats on the left. So there's going to be different ways of solving this. One way would be to just ignore the problem like I originally did and just go back to %i. Or, as an aside, %d is often an alternative to %i for a decimal number. But we use %i because it sounds like int. So %i is fine here, too. But I don't want to just avoid the problem. I want to actually display a floating point value. So how can I fix this? Well, it turns out I can solve this in a few different ways. The simplest is just to make sure that at least one number on the right is a floating point value, like 3.0 instead of just 3. Now, I think Clang will be happier. Let me do make scores, enter. And indeed, it's OK. Why? As soon as you have at least one more precise data type on the right, it just treats everything at that point as floating point values so that the math works out. So /scores, enter. And now, there we go, right? You know, some of us might really want that third of a point. Our average was not 59. It's 59 1/3, as in this case here. All right, so we've solved that there. As an aside, though, there's one other technique to show here. If you didn't want to change it to 3.0, because that's a little weird, because there were literally 3 scores. It's not like that needs to have a decimal point. You could also explicitly convert the 3 to a float by saying in parentheses float. This is what's called typecasting. And this will just convert the thing right after it to that data type, if it's possible. So if I do this again, make scores, no errors now, /scores, and I get, in fact, the same result. There's a bit of a rounding issue here, but we know the rounding relates to the imprecision from last week. For now, let me just be happy with my 59.3 something. I'll take that for now. But this is, you know, as close to a good enough correct answer for me now. But how do I think about now what's going on inside of the computer's memory? Well, let's consider. Here's that same grid of memory. Each box represents a byte. Where are score 1, score 2, and score 3 in my memory? Well, score 1, let me just propose, is at the top left. But it's taking up 4 boxes for 4 bytes. Score 2 probably ends up right next to it in memory, though this isn't always going to be the case. But I've chosen simple examples. 73 is next to it, also taking up 4 bytes. And then lastly, 33 is in score 3 down there underneath. Now, if we really look at the computer's memory, look at it with some kind of microscope or the like, there's actually 32 bits, 32 bits, 32 bits in each of those 4 groups of 4 bytes representing those values. But again, for today's purposes onwards, we don't really need to think again and again in binary. It's just indeed these decimal numbers being stored there. But I claim now this isn't the best design. Even if you had never programmed before CS50, what you're looking at here on the screen as an excerpt, in what sense is this perhaps bad design, even though it's a correct way of storing 3 test scores? What's kind of bad here? Yeah? Yeah, always do exactly what you did. Extrapolate to 4 scores, 5 scores, 50 scores. This can't be that well designed, because now you're going to have 4 lines of code, 5 lines of code, 50 lines of code that are almost identical, except for this like arbitrary number that we're updating at the end of the variable. So indeed, there's probably going to be a better way, even though, at least in C, we haven't yet seen that technique. But the solution today onward is going to be something called an array. An array is a way of storing your data back to back to back in the computer's memory in such a way that you can access each individual member easily. Put another way, with an array, you can instead do something like this. Instead of saying int score 1, int score 2, int score 3, giving each a value, you can first tell the computer, please give me a variable called scores, plural, though you can call it anything you want, of size 3, each of which will be an integer. That is to say, this is how you declare an array in C that will have enough room to store 3 integers. Put another way, this is the technical way of telling the computer, please give me 12 bytes in total. 3 times 4 each for an int, so give me 12 bytes in total. And what the computer will do is guarantee that they're back to back to back in the computer's memory. And that'll be useful in just a moment. So let me go ahead and do something useful with this. Let me store 3 actual scores. Here's how I could now store those same numeric scores in this array. Syntax is a little different, but there's one variable called scores. But if you want to go to its first location, starting today, you use square brackets and go to location 0 first, which, because things in C are 0 indexed, so to speak, you start counting at 0. The first int is at bracket 0. Second int is at bracket 1. Third int is at bracket 2. So it's not 1, 2, 3. It's literally 0, 1, 2. And this is not something you have control over. You must start at 0. So these lines now create an array of size 3, and then insert 1, 2, 3 values into that array. But the upside now is that you only have one name of the variable to remember. It's just called scores. Yes, you need to go into the array to get individual values. You need to index into it using those square brackets, but at least you don't have this hackish approach of declaring a separate variable for each and every one of these values. So let me go back to scores .c here. And let me propose that I do this. Let me just kind of use that same idea to do the following. Let me get rid of these 3 separate integers. Let me give myself an int scores array of size 3. And then scores bracket 0 will, as before, be 72. Scores bracket 1 will be 73. And scores bracket 2 will be 33. And let me get rid of the little dot there. All right, so now if I go ahead and run this again with make scores, enter. What did I do wrong here? I think I got a little too ahead of myself. Let me increase my terminal window. Let's focus on line 10 here first. Error, use of undeclared identifier score 1. What did I do here that was dumb? Yeah. Right, so I didn't declare score 1. I've got old code, right? So I just kind of honestly got ahead of myself here, not even intentionally. So let me go ahead and shrink my terminal window again. I need to finish my thought here. So let me clear my terminal. And let me change this now to be scores bracket 0 plus scores bracket 1 plus scores bracket 2. So it's a little more verbose because I've got these square brackets, so to speak. But I think now my code is consistent. So let me make scores now. It now compiles. /scores gives me indeed the same rough average with those same values. All right, so let me go ahead and maybe enhance this a little bit. It's a little silly to have to write a special program just to check your average of 3 test scores, like 72, 73, 33. Why don't I actually make the program dynamic and ask the human for that average, for those scores? So instead, let me do this. How about we get rid of the 72 and change this to getInt, and I'll just prompt the user for a score. Let me get rid of the 33 and change 73 and get this to be getInt score, quote unquote. And then lastly, get rid of the 33 and replace it with getInt, quote unquote, score. GetInt is a CS50 thing for now, so I need to include CS50.h as always. But I think now it's sort of a better program because now I can compile it once. I can even share it with my friends. And now any of us can average 3 scores on some class's test. They don't need to know the code or rewrite the code just to type in their scores. So make scores, worked, /scores. Now I can type anything I want. Maybe it's a 72, 73, 33. Still get the same answer. Or maybe I'm having a better semester, 100, 100, maybe 99. And now we get still a pretty high score there. But now it's dynamic. Now you don't need the source code. You don't need to recompile the program. It's just going to work again and again. But this too, let me propose that this code is correct if I want to get 3 scores from the user. But these highlighted lines now, 6 through 9, are they well designed, would you say? Yeah. Yeah, right? We can use a loop is the spoiler here. Why? I mean, my God, it's like the same code again and again and again. The only thing that's changing is the number. And it should have kind of had some code smell again, because if I keep typing the same thing again and again, like that's clearly an opportunity to better design something. So let me do this. Let me go ahead and still create my array of size 3. But let me use our old friend, the for loop, for int I equals 0. I less than 3, I plus plus, and then in here, let me do scores bracket. We haven't seen this before, but any intuition? Scores bracket I, because that will use whatever I is, be it 0 or 1 or 2 in iteration, and then I can get an int asking the user for score without having to repeat myself again and again. So hopefully, if I didn't make any typos, make scores. All good. /scores, 72, 73, 33, and we're back in business. But the code is arguably now better designed because now I haven't actually hard-coded the scores, and I haven't actually copied and pasted any of that code. Well, if we consider now what's going on inside of the computer's memory, it's pretty much the same in terms of the values. But instead of the variables being literally score 1, score 2, score 3, there's just one variable. It's an array called scores, but you can index into its 3 locations by using scores bracket 0 to get the first, scores bracket 1 to get the second, scores bracket 2 to get the third. But this is key. The memory is contiguous. It's only the screen is only so large, so it wraps around. But physically, digitally, the memory is contiguous, top to bottom, left to right. And that's important. Why? Because the brackets indicate 0, 1, 2, that each of these integers is just one integer away from the next. It can't be randomly down here all of a sudden. It's got to be back to back to back. All right, now equipped with that paradigm, what more could we actually do here? Well, it turns out it's worth knowing that it's possible in code to even pass arrays around as arguments. And let me just whip this program up somewhat quickly just so you've seen it before long. But let me go ahead and do this. Let me propose that I create a function that does this averaging for me. So I'm going to create a function called average that returns a float. And the arguments this thing is going to take, let's see, it's going to be the array. So it turns out if you want to take in an array of numbers, you can call it anything you want. This is how you tell C that a function takes not an integer, but an array of integers. And you don't have to call it array. I'm doing that just for the sake of discussion. It can be called x. It can be numbers. It can be anything else. I'm just calling it array to be super explicit as to what it is there. Now, how do I change my code down here? What I think I'm going to do for the moment is just this. I'm going to get rid of this code here where I manually computed the average. And let me just call the average function here by passing in the whole array of scores. So this is just an example of abstraction. Like now I have a function called average. I don't care. I don't have to remember how it works once I implement it. And it just kind of tightens up my main code a little bit. But I do still have to implement this. So later in my file, let me repeat myself before. The only time it's OK in C to repeat yourself again and again by typing out again average and then int array open bracket. But now not a semicolon. Now I have to implement this thing. And I can implement this in a bunch of different ways. But I don't know, in advance, I can't just do this. I can't just do array bracket 0 plus array bracket 1 plus array bracket 2, unless this program's only ever going to work on 3 numbers. So, let me go ahead and do this. Let me first propose that there's a poor design here. In my main function, what value have I repeated twice? Among the highlighted lines, what jumps out at you as twice? Yeah, the length of the array is just 3. Now, it's not a huge deal that I type the number 3 on line 8, on line 9. But this is exactly the kind of like shortcut that's going to get you in trouble eventually. Why? Because eventually you or someone else is going to go in, make the array bigger or smaller. And you're not going to realize that magically that same number is in 2 places. And indeed, this is what a programmer would often call a magic number. A magic number is one that just kind of appears magically. And you're on the honor system to change it here if you change it here. And then you change it over here. Like, that's not going to end well if the onus is on the programmer to remember where they hard-coded, that is, wrote out 3 explicitly. So anytime you reuse a value like this, you know what? We should probably do what we did last week, which was to declare a variable, perhaps at the very top of my program, so it's super obvious what it is, called maybe n, and set that equal to 3. Better yet, what did I do last week to make sure that I can't screw up and accidentally change that value? Yeah, constant. And the keyword there was just const for short. And now I have a global variable, global in the sense that I can access it anywhere, that is called n. It's an int, and it's always going to be 3. And now I can improve my main function a little bit by just changing the 3's to n. So now if a colleague realizes, oh, wait a minute, there's 4 tests this year, you change n to 4, recompile the code, and it just works everywhere else. Except in my average function. Let me change it back to 3, just for consistency. This is not going to fly now to just sum up things like this, for instance, and then return this divided by 3. Why will this not work now, as I've defined it? Yeah. OK, I might be returning an integer value when I intend to return a float per this. But I think I'm OK, because I used that little trick where I made sure that at least one of the numbers in my arithmetic expression is, in fact, a floating point value. And just by adding the point 0, make sure that everything gets treated as a float. So I think that's OK. Oh, sorry, a little louder? Exactly. So left hand's not talking to the right hand here, in that my current implementation of average is still assuming that there's only going to be 3 tests or whatever. But wait a minute, I just went through the trouble of modifying this to be n generically. And if I change this to 4, I'm not going to be happy perhaps with my average, because now I'm going to ignore one of my test scores altogether. So let me change this back to 3. And unfortunately, if it's a variable now n, and therefore I have literally a variable number of scores, how do I take the average of a variable number of things? I mean, what's my building block there? Yeah? Yeah, why don't I use a loop that goes through the array and adds things up as you go? I mean, kind of like grade school. As you take the average on your calculator or paper pencil, you just keep adding the numbers together, and then you divide at the end by the total number of things. So how can I do this? Well, let me change my implementation of average to first declare a variable called sum or whatever, set it equal to 0. So this is like me on my piece of paper getting ready to count, or my calculator, of course, when you turn it on, typically defaults to 0. And now let me do for int I equals 0. I is less than a nope, I didn't do that. N, I is less than n, I plus plus. And now in here, let me go ahead and add to the current sum whatever is in the array's location I. And then down here, I think I can just return sum divided by 3.0 n. Perhaps here. And actually, I think I'm going to get, let's make sure it's a float. Let's use the typecasting trick just to make sure I don't accidentally shortchange someone and throw away everything after the decimal point. So it just escalated quickly, right? Like average just got a lot more involved. It's not just a single one line of code, but now it's dynamic. I initialize a variable called sum to 0. In this loop, I go through and just keep adding to sum, which is initially 0, whatever's in array bracket I, or specifically array bracket 0, array bracket 1, array bracket 2. That gives me a total sum that I return divided by the total number of things. Now this I can tighten slightly. Recall that this is syntactic sugar for just adding things. I can't use plus plus because that only literally adds 1, but I can use here plus equals. Questions on this implementation here? Really, the only takeaway, or the most important takeaway, is that this is the syntax for how you tell a function that it expects a whole array, not a single variable like an int or the like. You literally use square brackets, but you don't specify the length inside there. Yeah? What about the variable at the top? Good question. What do I have it defined as at the top? This variable n, it must be an integer if you're going to use it inside of an array's square brackets here. So this line 10, notice, no longer says 3. It says n. And so whatever n is, 3 or 4 or something else, that's how many integers I will get in that array. And it must be, by definition of an array, an integer that goes in those square brackets. And here's a common source of confusion. When you create the array, that is, declare it, you use square brackets like this, where you put the total number of elements you want. When you subsequently use the array, like I'm doing here, you don't mention int again, just like you don't mention int again and again once a variable exists. You use the square brackets still, but you don't use n. You use 0 or 1 or 2, or generically here, I. So when C was designed, they sometimes use the same syntax for two different ideas or contexts. Yeah? Good question. Do I have to include line 6? Short answer, yes, because of the reason we ran into last week. C, or Clang really, reads your code top to bottom, left to right. And so if the compiler sees some mention of this function average on line 16, but you haven't told the compiler that average exists, you're going to get an error on the screen. So the conventional way to do that is you just copy paste the one first line of code from the function. It's so-called prototype or declaration. Yeah? Really good question and a perfect segue. Is there a library you can use if you don't know the size of the array? No. And so if any of you have programmed in Java or Python or other languages, you can actually just ask the array, like, how big is it? In C, you and I, the programmers, have to remember it. And so short answer, no. There's no function that will just automatically do this for us. And in fact, let me make a more subtle claim that it's fine to use global variables like this if they're really for configuration options. Why? It's just convenient to put them at the very top of the file because everyone, you, your colleagues, your TAs, are going to see them at the top of the code. But you really shouldn't be using them everywhere throughout your code. It'd be better if the average function itself were independent of that special variable. So by that I mean this. You know what I should really do if I really want to be well designed? I should pass in the length of the array to the average function. I should give the average function a second argument. I'll call it length, for instance, but I could call it anything I want. And so rather than putting n all the way down here at the bottom of my file, let me just dynamically say length instead. And this is a subtlety, and no need to get too tripped up over this. But this now is just an example of how the same function can take not one but two arguments. But indeed in C, you must remember yourself what the length of an array is. You can't just ask the array via some syntax like you can, those of you who've programmed before in Java or Python. Yeah? Good question. Would it be better designed to write a function that computes the size? Short answer, can't do that in C. As soon as you pass an array into a function in C, you cannot figure out its size if it's a generic array like that of integers. There are special cases that you can do that, but in general, no. It's just not possible in C. And if that's some frustration, honestly, this is why more modern languages add that feature. Why? Because it was really annoying, as I'm alluding here, to not having that information. Now, just to make sure I didn't screw up anywhere, let me compile this final version of scores. Suspense, all good, /scores, 72, 73, 33, and we're still back in business. So this version's more complicated, and as always, we'll have this version on the course's website for reference. But the point really is that arrays not only can be used as containers to store multiple values, 3 or more in this case, you can also even pass them around as arguments as such. All right.